All right. We've got some numbers and people start joining, but and I will start introducing the webinar and Tatiana, and we'll get started. Hopefully people will join in before Tatiana starts. So hello, good afternoon, everyone. Welcome to the first ever BTSYM webinar. And it's a great one to start with. We are going to listen to Tatiana Richa talk about innovative tool to predict surface settlement caused by tunnel construction. Tatiana completed her Ph.D. in 2023 on the use of machine learning to predict tunnel-induced settlement. Since then, she has focused on developing and promoting automation and AI to advance geotechnical engineering, and she's notably been involved with Orbo, a collaborative geotechnical web platform designed to manage large data sets and connect them to calculation tools. Floor is all yours, Tatiana. Please
Thank
go ahead.
you. Thank you, everyone, for connecting. Hello, everyone. I would like, first of all, to thank the young members of the British Tunneling Society for inviting me to talk about an innovative tool to predict surface settlements caused by tunnel construction. This was the work I did in my PhD, which I defended in 2023. The manuscript is available online. It's in French, however. The work was done under the supervision of Jean-Michel Pereira and Lina Guayacan from Laboratoire Navier of École des Ponts Paris-Tech, Gilles Chaperon from Terrasol Setec, Francis Lanquette from TPI Setec. And today I'm a product manager of Orbo and head of AI unit at Terrasol Setec. Allow me just one slide about Terrasol. So Setec is an engineering group of multidisciplinary consultants, and Terrasol is the geotechnical consulting firm in Setec. We work in France, and more than 30% of our work is abroad, internationally. We also have expertise in geotechnical softwares and development and marketing. Our latest is Orbo, and we also give geotechnical trainings to our fellows. Back to our subject. So the context is the Grand Paris Express, which is until today the largest metro project in Europe, with about 200 kilometers of new railway lines. In the context of my PhD, we had access to two lines, 14 South and 15 Southwest, which together formed about 13 kilometers of tunnel boring machine excavated lines. Specifically, it was an earth pressure balance TBM with a diameter of about 10 meters. The excavation was done in a very rich and varied stratigraphy, like you can see in the image below. As you all may know, the biggest risk in excavating underground in very dense areas is surface settlements. Today, we have traditional methods to calculate these settlements, like empirical methods who only give a rough estimate of the maximum settlement observed on top of the tunnel axis, or numerical methods like finite element calculations or discrete element calculations. However, these techniques take a lot of time to build the model, and for those of you who don't know, 3D modeling can take up to a few days to run all the calculations. So we understand that these methods are not sufficiently reactive today for our needs on the field. That's why we wanted to consider more innovative methods that can reduce the time needed to produce and update settlement predictions. We then thought about artificial intelligence, specifically machine learning, because we had the privilege of having a lot of data on the Grand Paris Express. And when I say a lot of data, I am talking about TBM operating parameters like the speed of excavation, the front pressure, the pressure of grout injected at the end of the shield, etc. And soil parameters, like the geotechnical parameters of each layer and the lithostratigraphy. And the most important is the monitoring data. We had monitors that were put on top, on the surface, to measure the settlements while the tunnel was excavating. What interests us in this work is to predict the Smax, the maximum settlement on top of the tunnel axis. So how do we get this value from monitoring data? What we did is that we fit the cumulative probability curve on the measures of each monitor of the settlements in respect to distance to tunnel face. So this would be a curve of each of these monitors. And therefore, once we fit this curve, we get the maximum value of settlement measured by this monitor. We note this parameter S star. And then we can plot all the S star values found in respect to the distance to tunnel axis, that being the distance to tunnel axis. And on these values, we can then fit the Gaussian curve, and that will let us predict the maximum let us find out the maximum settlement on top of the tunnel excavation. And that's how we were able to create and build our database on which we can then use machine learning to predict these settlements. So I conclude that we have TBM parameters, soil parameters, and SMAX. Now let's move on to the methodology of application of machine learning. So first of all, you have to choose your algorithms. In this work, we wanted to test XGBoost, random forest, artificial neural networks, decision trees, and support vector machine. Then you choose your metrics, the parameters that will help you measure the accuracy of the predictions. We wanted to test RMSE and R-square. There is simple comparison between the measured or real values and the predicted values using artificial intelligence. And that's how we can find out if the algorithm, or let's say the model obtained from the algorithm, is performant enough. And then we divide the data sets. It's a common way to divide it with the 80% of the data for training and validation and 20% for testing. So that leaves us with about 2,000 observations of maximum settlement values, TBM values, and soil values to train the algorithm and obtain a model. And then we have the 500 values to test the obtained model and check if it's capable of generalization. So it's capable to predict the maximum settlements on observations that the algorithm does not know at this point. As you can see in the image right here, the training and testing observations were selected randomly along the tunnel axis. That means that at this point of the work, we wanted to consider that the excavation is already done, that we have in our database the whole data. So we didn't take into consideration time and space. We will talk about that later on. Once we divide the data set, we can train the algorithm and verify for overfitting. I will not go into details, but for those of you who know a little bit of machine learning, we did cross-validation and we used learning curves. Here is an example of a learning curve using random forest algorithm. So what we do is we vary the data set size and we analyze the metric. In this case, we took R-square. You should know that the value of R-square near 0 is a very bad performant algorithm, and near 1 would be a perfect result. So we train the algorithm and we plot the results in black, and we do the cross-validation and plot the results in red. What we can conclude from this graph is that about 700 values were already enough to have a sufficient performance, because we can see that we reach a value of R-square near 0.9. So in respect to this conclusion, we can go back to the dataset division, and instead of taking 80% for the training, it was enough to take 30%, which leaves us with 777 observations, and let us have 70% for testing, which is amazing because we get to test our algorithm on more points. And then we regularize and optimize our algorithm. It's hard to go into details in a few minutes, so I will just say these for the people who have done already a little bit of machine learning. We used bias variance trade-off, and that way we were able to find optimum values and ranges of hyperparameters for each algorithm. And then we did a random search to find the optimum combination of all of these hyperparameters and the found ranges at first. So to resume that in a very simple sentence, it's just about optimizing the complexity of the algorithm in a way that it would be able to detect the correlations between the features, which are the tunnel parameters, the soil parameters, and the target, which is Smax. And finally, we analyzed the results. And like you see in the table on the left, we conclude that XGBoost and Random Forest had superior results to other algorithms and have exceeded a very good performance, even with a relatively small data set size. Now, let's go back to what I said before about the fact that we did not at first take the space and distance, the space and time into consideration. In reality, what is happening? Here I'm plotting line 14 south and the two sections of line 15 southwest, TR1 and TR2. In reality, we have a tunnel that is excavating, and we already have measured the settlements behind the tunnel face. And we want to use AI to predict the settlements in front of the tunnel face for the red points, where we don't already have settlement measurements. So that's the biggest difference between the exercise that we did before. What we did before was a kind of interpolation. We were looking to predict values that were already kind of seen in our algorithm. Whereas now we want to use old data to train the algorithm and then use the obtained model to predict the settlement in front of the tunnel face. So it's kind of an extrapolation. Now I'm going to show you a few exercises on how we did this real-time prediction. The first exercise I'm showing is that we took the first 1,000 meters of line TR1 of line 15 southwest for training. So that's about 173 observations for training. And then we wanted to use the obtained model to predict the settlements on the rest of the tunnel line. So what do we get? Here I am plotting the predicted maximum settlements in respect to the measured maximum settlements. We have the diagonal, which represents the perfect predictions because the value of the prediction is equal to the measured value. And we accepted an error of plus or minus 1 millimeter. In black, you have the points of the training. So we see that the algorithm did a very good training and gave us good training results. And then the colored points are the testing points. So it's all the points that are right here. What does the color represent? Well, you can see right here that it's the distance, the spatial extrapolation distance. So a value of 0 would mean that the point is right next to the tunnel face. And then we move to yellow, green, blue, and pink. Okay, so it's about how far away are we from the tunnel face. And what we can conclude from this graph is that the model was capable of doing very good predictions for points who are up to 300 meters away from the tunnel face, so in this area. And it was incapable of doing good enough predictions for the rest of the line. But you know, in this exercise, I waited like 1,000 meters to train an algorithm. In reality, when a tunnel is excavating, we don't want to wait that much until we get a functioning algorithm. So since on the Grand Paris Express, we had the chance of having many lines, we wanted to enrich our database using data from another line for the training of this algorithm. What does that mean? It means that we took all the data of line 14 south, and we took just the 500 meters of TR1, and we trained an algorithm using this database. So we trained the algorithm with about 850 observations. And then we tried to use the obtained model to predict the rest of to predict the settlements on the rest of the line. And we found out that enriching the database with data in similar conditions is a very good way to obtain a performing model. Because I have to remind you that both lines are very close to each other. So we have same TBM excavation, we have EPB excavation, and we have similar soil conditions. So that's why it was useful to do that kind of predictions. And then we wanted to go even further with our work and try a monthly training. What does that mean? It means that I fixed the dates and I looked at this date, what are the data that I already have in my database, which means until what part did the tunnel already excavate on the three lines, TR1, TR2, and line 14 south. I took all the data that is already available at this date, I trained the algorithm with it, and then I used the obtained model to predict the rest of the settlements on the TR1. And that's the result we see. It's logical. We have more and more points when we move forward in time. And we see that in about 8 months of excavation, we already have a very performant model that is capable of predicting settlements. And to be on the safest side, we would recommend to use this model in this specific work up to 150 meters in front of the tunnel face to predict the settlements instead of 300 meters. Now I would like to raise a point about the extrapolation. You should know that for machine learning, it is well known that these methods are not really capable of statistical extrapolation. What does that mean? It means that if we use the obtained model to predict on values that are not known or seen by the algorithm with the training, we know that the model will not be performant. Until today, they are not capable of doing that. But in our case, we are not really trying to do statistical extrapolation. We're trying to do spatial extrapolation because we are trying to predict like 30 or 100 meters in front of the tunnel face. So we consider that the conditions, the TBM operating parameters and the soil conditions will not be so different from what was already seen behind the tunnel face. And that's really important to distinguish between these two. And that's why we expect our model to be performant, because we're only doing spatial extrapolation and not statistical extrapolation. So, of course, you can conclude from that that if you train your algorithm on a specific tunnel line and you try to use the obtained model on another tunnel line in another region, you will not have good performances. Now, I would like to remind you that behind all machine learning work, there are lots of challenges related to the data. Because in our case, we did not generate data based on clean models. No, we had field data. And field data is raw data that needs a lot of work to become exploitable, usable by machine learning algorithms. You have to consider that the data extraction, treatment, and cleaning and structuring of the data takes up to 80% of the time needed until we obtain the final machine learning model. So these are problems that should not be ignored. Other challenges are the fact that there are always many suppliers of the data. So in my case, I had a different supplier for the soil data, and another for the TBM data, and yet another for the settlement data. And that raises the question of the property and confidentiality of the data. Do I have the right to use this data? Do I have the right to build a model based on it? Can I share it, etc.? And the last problem was the diversity of the formats. So some would give us images, others CSV, others API. So we were a bit all over the place with all the files. What we would recommend is to impose a universal data access mode like databases or interfaces in a structured format that would help have a better data sharing processes. So at Terrasol, we wanted to make that happen by developing Orbo. It's our new geotechnical collaborative web platform, which is designed to meet the needs of all players in the geotechnical field. It answers the need of having all the project information digitalized in one place in a structured format, which can be shared or not with your fellow colleagues and partners. Having such a structured platform saves us up to 80% of the unbearable tasks of data preparation for machine learning. So now I will pass to a small demo of a module that I built on Orbo. So when you open Orbo, you're gonna fall on the map of your company. Here I'm in the domain of Terrasol. We have a very big library of calculation tools connected to Orbo. And right now, what I want to show you is Tunnelia, which is an AI tool for the prediction of tunnel settlements. This is the first time I actually show this tool. I published it in about 1 month. Sorry, it's still in French. Let me go back to English. Excuse me, just a second. Perfect. So as soon as we go into this application, we can connect to the database. Then we select the lines that we want to work with. It's interactive, so we see right away the differences. And then we go to the features. The target is fixed to maximum settlements at the tunnel axis. I would love to add in the next upgrade the maximum settlements at a certain distance from the tunnel axis, which is as a star. And then you can select the features that you would like to add to your work. Let's select all of them. We import the database, and it opens up a data visualization tab. Right here, I'm going to show you the longitudinal profile of the soil of TR1. Then we do some statistical work, which means that we're going to look at the mean, the standard deviation, minimum, maximum, and the quantile of all the features, as well as the target. We can check out histograms to check the division of data. That's not enough. There you go. Scatter plots. So that way we can see if visually if two parameters are correlated. And we can even add a third parameter by using the color. We can plot box plots. For those who don't know, box plots help us figure out if our data has any outliers in it. And then the heat map, which helps us put the Pearson correlation between all the inputs and the outputs. And then we can do data division. So here I see that I have 1,000 values for the sample, for the training sample. Let's go into something a bit more smaller, 700 for the training and 500 for the testing. I see the data distribution on the right, so I can already tell that all my test data has already been seen in the training sets, right? So I know that I'm not doing any statistical extrapolation. I'm cross-validation, we can change the number of folds. Machine learning algorithms. I gave here just a few hyperparameters. Remember when I said we optimize the hyperparameter of the algorithm? Well, here they are. The training takes less than 10 seconds. And then we can analyze the machine learning results. So here are the plots that I already showed you. We have the training data. The score is 0.99 and the test score is 0.95. So I know that it worked very well. If I want to see what is the difference, maximum difference between the measured settlement and the predicted settlement, we can go to this plot. We see the residual. It's just the predicted minus the real values. And we see that mostly we have just an error of 1 millimeter. And it can go up to 2 millimeters, except for 2 points who did bad predictions. We can see the learning curves. And finally, the permutation importance plot, which shows the importance of each feature to the obtained model. And here we can see that it's mostly soil parameters that had the biggest influence. Last thing, and very fast, we can do also real case predictions. So here I'm going to do the exact same thing that I showed you. We're going to take just 500 meters of the first TR1 for the training. So this is the tunnel face. I consider that the tunnel face is here, and I want to predict all the rest. And here I took all of this for the training, and I can verify that what I did is right because I have 428 samples for training. Let's take a little bit more for testing. We have 67. And here are the distributions, train the algorithm. I need 20 more seconds and I'll be done with my presentation. And then we can analyze the prediction versus the real values. So yeah, that's everything I wanted to show you today. Thank you for listening, and please don't hesitate if you have any questions.
Thank you so much, Tatiana. Yes, if you've got any questions, please feel free to drop it in the chat or the Q&A. And actually, we already have one question from Kapil Sharma. What statistical tool is used to train the model? R programming or Python?
I used Python for everything, the statistical parts and the machine learning parts. And I would recommend R as well for statistical work. But once I wanted to use machine learning libraries, scikit-learn is really one of the best open source options that are out there.
Thank you. Jonathan, I think you had raised your hand. I'm not sure if you can ask the question, but feel free to drop it in the chat. And kind of while we're waiting for Jonathan, I had a quick question as well, Tatiana. It was just, you may have answered this in your last bit, but in terms of ground types, is there a certain ground type where you found it a lot harder to train the machine using those data sets or kind of getting the right accuracy?
Actually, it's not about the ground type. It's about, has the algorithm already seen this ground type and the training or not? If it has already seen it, even if it's complicated types, there is no problems with that. So typically, one example I did in my PhD was train the algorithm up until here, until 3000, and I tried to predict the rest. And right as soon as it gets into this soil layer that it did not see before, the results were not good because it's a soil type that it has never seen. It does not know it. So I'm trying to ask the algorithm to do a statistical extrapolation, which he's not capable of.
I see. That's fascinating, though. I think because we're quite close to 1 o'clock, I'll stop here. Before you leave, I just very quickly wanted to go through some of our upcoming events. So I'll just share my screen really quickly. So coming up on the 8th of March, on the 6th of March, we'll be celebrating International Women's Day. For that event, we've got planned a lecture, first of all, on BREEAM, on best practice sustainability frameworks. They'll be presented by two directors, Emma Jones and Rachel Jones from Ramble. Following the presentation, we want to hold a networking session between all engineers. So we just want to clarify that all engineers are very welcome to attend this session and just kind of help network with senior women in our industry. If you are a woman in tunneling, we really encourage you to kind of send over any kind of stories or inspiring quotes or things like that from your time in the industry. What we would like to build is kind of like a digital collage just celebrating women in tunneling. And then the event following that is we started our sustainability sessions. So the first one happened this month, and it was on the early stages of a project. The second session will take place in Leeds, and it'll be focusing more on the design and construction element. You can also join online. So of course you don't have to be in Leeds to attend. So if you're in Leeds, we really encourage you to come join us in person. But if you're not, then please register for the online link. That's everything from me. And yeah, again, just wanted to say thank you so much, Tatiana.
Thank you
And
for the
your
invitation.
module, sorry, the module that you shared, do you mind like giving us a link we can share out with the attendees or something so they can play
Of
around?
course. Actually, it's integrated into Orbo. So whoever likes to try it, I can easily give you a free access for about a month. And that way you can try the Orbo interface, all of it. And yeah, we can discuss all of that. That's definitely
Brilliant.
doable.
Thank you so much.